but we can talk about that. You saw the oil. You can buy them from like Canon, nothing fancy. We'll go into that later. But you have one instrument cal that we're going to do first. That calibration is done with no fixture on. All right. If you do it with fixture on, it's not going to like blow up the system or anything. But you might throw an error when you go to do your actually start a run because if you end up with a negative geometry inertia, the software is like that's not possible. This can't be a thing, and you'll just start getting errors. It's not actually broken, it's just confused because you had something attached, right? So free spindle, nothing on it. Then you're gonna come in to the software, you're gonna go to the calibration tab, and then you're gonna go to the instrument tab in calibration. In here, there's only one, it's the inertia calibration. You're gonna click the little drop down, and you're gonna hit calibrate. And it does tell you there's a little like readout that says, hey, make sure that there's nothing attached right now. It's pretty quick, it doesn't take long.
So nothing's set up, just turn everything on and then go straight.
Nothing's on it, nothing's on it. We don't want anything on it. This is basically figuring out, so like before we said, right, so this is a combined motor transducer. So we need to figure out what the instrument's inertia is to take it out, so we can figure out what the material is doing. That's what we're doing right here. So you get a value, it should be 21-ish. This number is going to vary a little bit from run to run. Like if you run this 10 times, it'll shift a little bit, but about 21 is correct. So we would hit accept, and that value is now saved. Great. Now you're going to grab my cone because we're working with oil, so cone's probably going to be a little bit easier, and you're going to put it onto the machine.
How old do you need to go out on?
I mean, like long term is probably a good idea too for the purpose of training. That's just to keep like the oils from your fingers if something were to mess with it. For you guys, very important, you're only going to tighten from the top. You're not going to twist the bottom. You're just going to push the bottom on, tighten from the top to lock it onto the bearing. And you're not going to crank it. You got really big arms, so I know you hit the gym. Do not crank this thing down. It's going to, yeah, you want it snug, but don't crank it. Got it on. Great. The next thing I'd recommend that you do is you go ahead and set up the actual temperature for our plate to get that starting to heat through. So you can do that in a few different places. It's pretty easy. You can come onto the touchscreen, hit the little thermometer icon in the bottom, type in whatever temperature you want. We're just going to do 25 for the purposes of ease, and we'll hit apply. And then you'll start to see it heat up. While that's heating, we're going to go ahead and start the actual geometry calibrations. That way it soaks through, gets a temperature, and it kind of equilibrates before we go and gap. Or zero the gap, I should say.
So those are done automatically? Calibration, so geometry calibration?
They're not done automatically. We're going to go and do them now, but while we're doing it, we want it to kind of heat up. Because if we go and we zero the gap while it's at room temperature and then we heat it to 30 degrees or cool it to 10, we're going to have issues because that gap's going to shift slightly. And while it might not matter as much for other techniques, that distance between the plates is really important here, particularly because we're using a cone. Parallel plate, we have a millimeter. If it's 5 microns off, that's not great, but it's okay. Here, we only have 50 microns of distance between that point. If you're off by 5 microns, you are dramatically changing things. So you'll really notice it with the cone. So we want to be precise with this one. So from there, I'll have you steal. So you're going to go to the top where we had, like before you saw the geometry section there, you can calibrate there. Yep, that's the one. Now, you'll double check, make sure you're on the right selection. So here you have service 40 millimeters, so this is correct. This won't always be an issue. For yours, it'll actually have a barcode when you go and buy them so that it can read it. Mine's an older design, so we have to manually tell it what it is. But we'll get into this screen. So now we're going to do the geometry inertia. So you'll just go right down the list. You will not have to do the gap temperature while these are running. We'll chat. So if you want to go ahead, click the calibration drop down for inertia. So it's right there, yep. And then hit calibrate. So this is the exact same calibration we did for the instrument, but now with, if you want to scooch in so you can, it's going to do it with the geometry attached and figure out how much that geometry is impacting the inertia of the bearing. This value is going to shift depending on what you have, because obviously if it's stainless steel or if it's wider, physics exists and you'll have more impact. Of course, if you have a much smaller one, It's made out of aluminum. It's lighter. You get the
This calibration is different from the one we just did.
yes. Well, it's the same, but with the geometry on versus not on.
Oh, okay.
This is basically so that, like, hey, we can get the instruments out of the way, and now when we switch geometries, we'll redo it for each one if you were to have them.
Got it.
Yeah. So you can hit accept on that. Then you would do friction. Yeah, you know.
So if we finish measuring one sample, clean, back in, we do the same thing. Right?
Not if you leave the fixture in place. So if you take the fixture back off, yeah, you want to redo them. If you leave it in place, you should be okay. But the only time you take it off, so we were talking about curing materials before, it might be that when when it cures, those two plates are now like basically epoxied onto each other, right? And you're gonna have to kind of detach it, send the head up, and then work it off. Ideally, if you're doing something like that, you use disposable plates, so that way you can just kind of pull them off and maybe try and like soak them in a bath or something to like get rid of it or throw them away, whatever it might be. A little different. So just hit accept, and it should be like pretty close to 0 for this one because it's friction. Ideally, there's not much.
So 5% around-ish.
0.2, like 0.3 is micro newtons, whatever. So the rotational mapping is our last one. You can do different versions of this, like there's a more precise version. We're just gonna do standard in one iteration. The more that you do, like the more accurate you can be, but of course it takes longer for the purpose of training. We're not gonna do that, you just need to calculate. Basically, it's gonna go and map the encoder distance at the top and look at all the lines and figure out pretty much the position of the geometry. This is the really big one that if you take it off, this one's completely void now when you go put it back on, because you're not gonna put it on 100% completely the same way. So this mapping is not valid. I have had people still get OK data when they do it. I don't recommend it. I recommend you just rerun the rotation mapping for best.
So right now, this is kind of there's like.
Yes, and it needs to be for all three of these.
So do they? I assume when they do the measurement, it will go down.
Yes,
right?
and we're also going to zero that gap before we actually do measurements. So once this is done.
Yeah. So after you remove it, so how many returns to this location? Or?
I just move the head up. You can tell it there is a position that will go up by itself, but you can also just use the arrows in the front of the machine to send the head up and down.
It doesn't matter the distance.
No, just needs to be free to move. Like it couldn't be touching the bottom plate or anything like that. So to talk about that gap temperature compensation, we were talking before about temperature ramps being a possibility, so you can heat up the material and see how it behaves. When that happens, as you heat, your plates expand, right? We need to compensate for that. So basically what the gap temperature compensation does is it'll push the head down and then heat through that cycle. So you basically, you're going to set a rate, you're going to set a range, like you would on DSC, and have it heat through that, and basically it'll build a curve to adjust the height to keep the gap the best that it can. Very important notes with this, you really only want to do that with a parallel plate, because it's not a perfect calibration. There's going to be some error, and that error is probably only a few microns. So if you have 1,000 microns of distance, a few microns isn't necessarily going to be a massive issue. But with a cone, you tend to not want to do this as much because you're going to introduce error. Because as that expansion occurs, I mean, sure, it'll move away, but it might not be enough. And well, if it's 3 off, now you're looking at 10% versus like a 1 or 2% change, right? So ideally, you don't run a cone with this. You would just do it parallel plates, which is all you have right now. But it still exists, so you can try it. Just know that your error will go up a little bit if you're doing it with a cone. And you might notice if you have really tight differences between your materials that it doesn't necessarily stack up the way that you expected it, and you might have to change out to a different fixture to compensate. All right. So once the rotational is done, it won't ask you to accept; it just applies it, and we're good. So those are the geometry calibrations. So we only have one more calibration to do, and that is to just zero the gap. So what you can go ahead and do from this screen or from over here, if you're over here, you can just hit this little button with the 0 and the enter line, and it'll do it. Before you hit it, I recommend that you bring it a lot closer, especially if it doesn't know where it is. It goes really, really, really slow, and if we're super far away, it'll be annoying and it'll take a while. So we're just gonna send it down a little bit.
So this is before you put a sample?
Yes. You don't want to have the sample because it's going to go ahead and like completely crush whatever you have. So you get it closer, and then you can do it there. You can also do it in the software, but for the purpose of this, I would just hit the button there. Now, once it zeros, you'll see the distance at the top of the display. It'll come down, and then it'll move itself away to about 100 microns, and then go back to you're good to go.
So if this is a cone plate, so this basically the tip of the cone touching the
No, it's actually, so it is a cone, but the tip of the cone's sliced off. So if you looked at it, it's all there, and there's just like one little nub in the middle, because that way it's not actually touching. So cone is mostly correct. There's probably a term for that. I don't know what the term for a cone with the tip cut off is, but yeah. I'm sure somebody in math knows it, and they'd be very mad that I don't, but I'm not a mathematician, so.
That's pretty bad.
Yeah, right.
So we've gone back to about 100 microns, so it should be done now. So you can go ahead and move the head back up.
So after we zero it, we just need to.
Yeah, if you do it from over here, it'll actually go through like a calibrating. Like it'll tell you that, and when it goes back to idle, you're good. Here, you just kind of wait for it to go back to 100 for a second, and then you can move it. Not right now, because we're not doing impedance testing. Yeah, if we were doing impedance testing, we would. Right now, we're just doing like the basic testing, and we'll talk about that. Give yourself a little more space. We don't want to load a sample on there. Cool. So now you're gonna want gloves, because you're gonna be messing with whatever pure temp 23N red is. I hope it's not dangerous. I don't think it is, probably. Right? Cool. So now what you're doing, you get your pipette wherever that disappeared to, or here, and you're just gonna get a good amount of it in there.
What if it's too much?
That's okay. We'll clean it. Well, and that'll be a step we'll do in a second. You're just gonna put it right on the center and just make kind of a nice, good amount of it. Yeah, exactly. Exactly. Cool. That should be good. And what I'm actually gonna do, it could be good to cool it down a little bit to get it to be a little bit thicker, but it'll be fine. The measurement might be so-so just because it is kind of thin. It's hard to gauge that until it's sitting there flowing. From there, if you had a thicker material like a gel or something like that, you would go to the trim gap, right? So before we talked about this. Now, if you went to the trim gaps, you can tell that's not going to do anything, right? So the trim gap, so we have a normal operating distance, the distance between the two plates when we're actually doing a measurement, all right? That's a geometry gap, testing gap, truncation gap. They all mean the same thing, operating gap, right? But for thicker materials like PDMS, something like that, you have what we call a trim gap offset. So first, you go to, typically it's about 5% above whatever your operating gap is, and that's where we're gonna clean it up and trim it. Before you were saying if there's too much, we will basically clean the excess, trim the excess off, and then start our experiment. Something's thicker, we go to the trim gap, we trim it down, and then we go to our operating gap. It'll basically squish it. Depends. So for this material, we're gonna use, where did that thing go? I said you could use it, but I may have lost it. So, oh, there it is. Put it in the wrong place. It's pretty much just a piece of plastic shim with a good 90 degree on it. So we were talking earlier, you could use like a credit card that you cut. You could use maybe one of those cheap cutting boards you get at Walmart that's like all floppy. Use one of those. Just something that's you can cut to get yourself a nice 90 degree angle. So that way when we kind of go around, it'll make a good like scraper.
Card or something.
Yeah, you bunch it around from something that's non-absorbent, of course, and then with a nice angle. We don't want to use like paper towels or anything, because you can actually pull some of the solution out from under the fixture, which will mess up the measurement. The goal is to basically have like a perfect cylinder with an asterisk there, but underneath the fixture. We don't want it to be like completely blown out. We don't want it to be too little under there, because that will impact our measurement. So
So you want to fully cover the base
of the cone, not of the bottom fixture. So you can go ahead and go to the geometry gap. Yeah. Perfect. What I'd probably do with this material, once it's good, so once these go back to being that color, I'm going to spin it a little bit, just to make sure that you kind of push any air bubbles out. Since this is a thinner solution, you can do that. If you had a solution that was much thicker, of course you can't really push them out like that. Just set it's like 1 rad per second. And it'll just start rotating on you. Just give it a minute or so. Again, it doesn't work for everything, and sometimes you might not want to do this because it's going to kind of pre-disturb your sample. But if you have like a really uniform, not suspension-based material, this is a pretty easy way to kind of force air bubbles out and that sort of thing. It doesn't work as well with the parallel plate. The cones that has kind of the sides of bubbles just kind of plus. In the situation that you have something thicker like that, the biggest thing is when you're placing the sample down, avoid creating air pockets in as much as possible, or kind of push them out if you can. It might mean you have to kind of reload a new batch of it, like clean it, put a new one on. If you just see a ton of air pockets, that's going to really mess with our accuracy. All right, what I would go ahead and do is stop the motor, then lock the motor. Then yeah, just give it 1 second. There you go. Cool. So the lock button went red, so you should be good. And now you got a paper towel and you got that. So start cleaning it.
So you just want to use that plastic to kind of scrape off.
Exactly.
And you don't want your paper towel to touch them.
Mm-hmm. Yeah. The paper towel is just to like make sure it doesn't go everywhere.
Like, you don't want to get close to
Yeah, but you don't want it like actually in there, because if it like sucks it out, then you might cause other issues. The nice thing with really liquidy stuff like this, especially like silicone models and things, you can kind of like put a drop next to it and spin it, and it'll kind of suck it up and fix your problem for you if you accidentally trim it too much. When we're trimming, we don't want to like really get under. We just want to go nicely around it. You're never going to get it perfect. That's not a thing that's going to happen. But like I was telling him earlier, one of the biggest sources of errors in this machine is the user. If you're not being consistent with the way that you load it, you're not being consistent with the way that you're calibrating and setting things up, you're going to see pretty big swings in your data, and it's not necessarily the machine couldn't be more accurate, but it's you need to increase that consistency of what you're doing. Just in terms of, hey, making sure that you're being consistent with your trimming, the way that you're zeroing, letting it equilibrate, those sorts of things, it's all really important for this system. Yeah, it's pretty good for how thin it is. Pretty darn good. So we're going to unlock that bearing. And then we're just going to set up a run. I think probably the simplest is going to be a peak cold on a flow, just for a simple viscosity check. If you wanted, we can do a bunch of different things. I find sometimes it can be really tough to dial it in, and it can take some time and kind of practicing. Something this liquidy, I don't want to do like a stress-controlled ramp, because if it doesn't get enough resistance, it'll just overspeed and then send that fluid flying. Not exactly ideal. So I'll have you come back over to the software here and go to the experiments tab. So first, just like you would in Trios and DSC, rename the sample to be like the 23N red demo. Cool. I'm not the operator. You are, so you should change.
So should I just go to the express first?
Sure, you can. Just click that back down. And you're the operator, so. If you want to change where that, or if you want to put whatever you want from the project in notes, but.
What is this thing about?
23 in.
That's right, in red.
You say training. Cool. You can change that file location. By default, it's just going into the data folder. But if you wanted to add one, again, just like the DSC, you could click the three little dots and change that.
Okay.
If you go into that geometry tab under there, here, there's not much you're gonna mess with. If you were to, like, if you're working with parallel plates and you wanted to adjust the gap, you would put it in here. The nice thing here too is if you have a very small amount of sample, it kind of gives you an idea of how much you need per run. Of course, you're going to use a teensy bit more because obviously you're going to overfill it a little bit. But it can give you an idea of like, okay, I've got 20 milliliters. I can run this, you know, like 10 times or so, and with pretty good efficiency. Because I don't know how to put 0.58 milliliters of anything onto anything consistently. But that's that. And of course, as you change the gap and stuff, that value will adjust too.
Okay.
So from there, we'll go into the procedure. Yeah. Yep. What we're gonna go ahead and do, if you hit the little feet with the X on it at the top there, all the way over to one more, that way, and just remove everything. We'll just start with a fresh blank slate. There's nothing here. So now you hit the little feet with the green on it, and that'll add a step. Beautiful. Like I said before, we're just going to do a simple flow peak hold. So you go to the slow option, and then you will go to peak hold. From there, we set the temperature, adjust that time to like 60 seconds. We don't want to sit here for 3 minutes. Normally, do more than 60 seconds, but A, it's sitting right now equilibrating, and B, we're training. We don't need to sit here for 3 minutes while it soaks. When you guys are actually doing this, 3 to 5 minutes is a pretty good amount of time to let it sit. So, looks great. From there, your duration, since we're just going to basically set a rate that we're going around, just set this duration for like 180 seconds. We'll just do 3 minutes. Then you would set the shear rate, but it might be easier instead of the shear rate. Yeah, so if you look at the little, like the drop, somewhere only going to have that option. That's fine. 1 revolution per second. That should be okay. No, that might be really fast. Try 0.5. Normally do it in rads per second, so this hurt my brain. Can you go to unlimited? I'm just interested if it's there. Unlimited. Like I said, it limits some of your options. It might give us rads if you drop down again. Yeah, there's velocity in rads per second. Let's just do it that way. And just do 1 rad per second. I know what that is. It's not going to send it flying. Sample interval, we probably don't need 1 second per point. We don't need 180 data points. Set it to be like 18 big, so just do 10. And you'll notice that it didn't really change much. You just had more under the hood, right? So it's kind of like, you can use unlimited, but Express, especially with something like completely new.
So for the unlimited and then express, like while I'm switching back and forth, my previous input is staying.
Depends on the input, because if the input isn't something that like can be switched over,
Okay.
it'll warn you and it might not be there.
Okay.
Because it'll just like default to whatever that value is.
So for like the velocity.
Yeah. And now what it might do is maintain the same number but convert it into one of the other rates. But yeah, that's it. So that's it run. At this point, you've cleaned it. It's at the right height. So you should be able to hit the start button. So it's already at 25, so it'll just wait for temperature for 10 seconds and then start equilibrating and just temperature soak for 60. And then it'll start spinning. So it's not going to be doing much of anything right now.
So the gap right now is about 46, 47.
Yeah, that's just a value specific to my cone. So on there, the truncation gap is listed. So that is the value that they're actually testing. So for the cone specifically, you get told the number. With a parallel plate, 1 millimeter is kind of the bog standard literature value. Some people do different, but that would be your average on that.
So the machine already knows once you...
Yes, because when I create the geometry in the software, I input that value.
You put that back. Yeah. So this is what we got now?
No, that's mine.
That's yours? Okay.
Yeah, you guys just have one parallel plate. It's all inside of this impedance box. Yeah, this is all that you have. It's a little different. I'm just showing you like the basics. The impedance kind of adds a layer of complexity to it, so I don't want to start there. I want to start simple, and then we're going to talk about this. Don't worry, but
Okay. So this one with impedance and regular
it's an impedance, and it's a parallel plate.
parallel plate. Okay.
Yeah.
I see.
We'll put it on in a second. We'll set it all up, but that's what you guys have. Of course, down the road you can get
How
more.
much is this one?
I wish I could tell you. those numbers fluctuate.
I'll ask one for it.
You gonna? I'm
So
sorry.
if you're giving a constant rate, then you're gonna got it. So viscosity is constant time.
Yeah, pretty much. It should be a flat line, right? If you see
If it's
a bunch of
non-
changes, yeah. Well, yeah. If you see a ton of change,
It's non-neutral.
there's something going on. Your temperature might be shifting or something like that. That's why you really want to let it sit for a few minutes before you start normally. In this case, of course, we were sitting here talking, so it's sitting in equilibrating, and we still gave it just a second. Ideally, when you're really running this and you're just kind of loading and running, you want to give it like 5 minutes to really let everything soak through, and then begin.
So when you set up over there, does it show the same thing over
Yeah,
here?
so if you come back to the home screen, you have procedure tab, and it'll tell you what it's doing. Now, of course, you don't normally want to really touch the screen very much when you're operating, because
Okay.
that vibration can be
Oh, I see.
problematic. I mean, you'd have to do a lot to really make it happen, like to see it, unless you're like right on the edges of what the machine can do. But
That's not.
normally, don't touch it.
Okay.
But again, this is a demo, so it really
Right.
doesn't matter.
So for this base plate, because you typically stay on, right? We don't take it off, clean
Mhm,
it.
mhm.
So you just wipe it off.
Yep, just with Kim wipes and acetone. You can, of course, take it off if you want, but you don't have to.
Typically.
Yeah, as you can see, it's kind of flown out after you did it because it's
Right.
just
Sure.
not very viscous. So it might be like, hey, you kind of have to test this at a lower temperature to make it thicken up a little bit or something like that. That sort of thing. Of course, there's also different fixtures you can use to help that as well.
What if it overflows over this plate? What do you mean?
You're not really using enough to where I'd be super worried that it's going to do a ton. If it does, clean it up. With a
Just wipe it off?
yeah, it's not going to like, as long as it doesn't like flow down and then in, which would be a bit tough, you're going to be okay.
Okay.
It's going to be a messy instrument by comparison to a lot of what you have regardless. Just, you know, there's all sorts of fluids flying around. You're going to see drips
Yeah,
all
I
over
was
the
just
thing.
wondering why they don't put it like a guard around the base plate.
Well, partially because in its current configuration, I want you guys to see it. There is a shield of sorts. It's not like airtight or anything.
This one?
Yeah, so when we go to the impedance, there is kind of like a heat band, and there's two little things that will sit around it. Here,
Okay.
that kind of acts like a cover, so they go around. They're not airtight or anything. But the other reason you don't want like a brim is it makes it harder to trim if it gets in the way. If that makes sense. Yep. So I have data. With this, because it is just hopefully one consistent line, you really just get the statistics off of it. Okay. So you would go into Analyze and grab whatever you're doing. In this case, we're just going to get statistics. So actually, I think we're going to have to do it a little differently. We can drag across, right-click, stamp, and then annotate with statistics, and that'll give us our average viscosity here, which unsurprisingly is pretty darn low. It's 0.017. For reference, the oil that you guys saw me playing with earlier is 1.07 Pascal seconds. So very thin, which is to be expected for the material, right? So now all you would do is you'd pick it back up, clean it, and then load the next one.
So for
Mm-hmm.
so you just like adding this points.
Yep. And you can go into like stamp, like if you want to know specifically what that point is, right? You can stamp it on there. Curve statistics is everything. Sometimes if you go up to analyzing, statistics will be just an option. I don't know why it doesn't exist when we're doing a peak hold, but whatever. But you know, hey, you can see signal change or whatever. So like if you were studying, like let's say you're doing a cure and you're leaving it at a constant temperature and you're just or well, probably vibrating back and forth, something like that, you might want to see, like, okay, from start to stop, how much did we see a change in that viscosity?
So for that one, I would just do the polynomial or something?
Well, if you're doing that, it might just be signal change. Yeah. Here, there's not going to be much signal change, hopefully. But, yeah. It would just be more of like if this didn't look flat and it was kind of curved or something like that. You know, there's different ways to analyze it depending on what you need to look
So
at.
can we program it, let's say, you set a certain speed and then after finishes, move on to the next speed? Or move on to
Yes,
the next
yes.
kind of
So what you could
conditions?
do, if you go back to the experiments tab, what you would do is you would click that little feet with the plus sign again, and it'll add a second step. And now you would go in and you would reset it, but put a new rate in. You do the same thing with temperatures too, if you wanted to. So you would have to do your gap temperature still, but you could go in and put like, hey, do it at 10, do it at 20. And that really is the most accurate way to do kind of a temperature curve. Right? We do something that is a temperature ramp where it's just consistently heating, and that's one step. But the material is not completely uniform during that time, so you're going to have a little bit more drift. So for your best data, you would do different steps, and then, or we actually have a function where it'll do that manually, so you do it this way as well.
So if you set like the temperature steps, you automatically wait until temperature stabilize and then move on.
Yeah, yeah, exactly. So if you did it like this, it would just, and you can make that happen with there is like a pre-programmed version of that. It's just an example we can set up. It'll, you'll say, hey, go to this temperature, soak for X amount of time, then measure for a minute, right? Move on to the next one, same example, rinse and repeat. That, of course, takes a lot more time because it has to sit and soak at each one, but it's going to be the most accurate data for you to build a curve out of in terms of material behavior on that.
So for that, let's say I want to soak for this time, keep it this temperature,
Mm-hmm.
and after this finish, can I automatically ask it maybe to ramp up the temperature?
Yeah, I mean, you can have it do a lot of things, yeah.
So where should I?
Well, you have to go to the second step.
Yeah, other different steps.
Yeah, and then now whatever you want it to do, you tell it to do. So if you want it to then equilibrate to 50, it can do the exact thing, you can do that. If you want it to be the exact same temperature, but we want to increase the rate. So I have some people that they want to know at like a low shear, a middle shear, and a high shear, how does the material behave? Is it different? And that's what they'll run.
So where is this then? No.
And what are you looking to change?
Let's say after this finish, I want equilibrium at 30 for a minute,
Okay,
and do it again for like 3 minutes.
sure. So you'd set flow. Nope, so nope, you're gonna go back to that step. You need to change it to flow. So you need to change from oscillation to flow now.
Ah, okay.
And then, so do it. And then now you would switch to be cold again. And then you would set it to be 30. And remember, there is that calibration we really should be doing in conjunction with this in terms of, like, we should be doing gap temperature compensation. That way it can compensate for that change. But, the simple, like, if you're actually setting up, this is what you would do. Now, you'd put in your duration, and you'd set the same shear, or well, you'd want to go and adjust it if you want the same rate and everything for that.
Mm-hmm.
So you click the drop down there, you go to your velocity, you'd set it to be 1, and then you set your duration for about, 3 minutes or so to let it kind of equilibrate. Because once it starts moving, it takes a second for everything to come to equilibrium as well. And then your sampling interval 10 seconds per point again. And it might actually be more interesting on this material if you set that to be like 10 degrees centigrade instead of 30, so you cool it, and you see the effect of that, or 15, whatever. Because it's going to become more viscous, ideally.
Okay.
And then, yeah. And so now it would go to 25, it would run it, then it would go to 10, it would run it, and if you wanted to keep changing it, you could do that. And what you'll basically end up with the plot is a bunch of lines, one for each temperature. If you're doing a temperature sweep, it looks kind of similar, but it's going to plot it.
So the data can export it into like Excel file.
Yes. Yep. So to export it, so you go back to results. When you have something pulled up, you click on the little icon at the top. There's an export option down at the bottom. And here you can put it right to a CSV or JSON, whatever you want to see.
Now you're programming a recipe for doing this. I was just wondering, like, do you have some standard recipe from your company that's targeting, for example, some low viscosity, medium viscosity, high viscosity material, or typical material that, because you are literally editing this recipe. And I previously saw somebody, they have a bunch of different recipes that we can follow so that we can get more high quality
So we talk to applications, and they can give you basic operations, right? They can give you kind of a starting point. Because it's going to depend on what you're testing and that sort of thing. Because there's low, medium, high, but also there's a pretty huge range of what you can kind of look at, right? But they can give you a starting point. From there, people that have a bunch of recipes, a lot of that's from like somebody sat there for years and on their materials and what they're working on, they came up with it. And then what you can do is when you come back to your experiments tab, you can save whatever procedure you have into a file and then pull that in later. That's what a lot of those people that have just like a bunch of them saved up for all of what they're testing. That's how they do it, right? They go and they get a base. You talk to applications. I'm not the best to help at that specifically, and you work from there basically, right? You take the basics and you go, okay, that worked pretty well. Let's maybe if I adjust, or maybe I don't need this high of a shear rate, or I don't need this full range like that. You can adjust, dial it in for your specific research, and then save it, and then keep on using it. That way, also, if you guys have like an undergrad that's working with you, that you kind of get basically trained up on it, you can just say like, hey, grab this procedure. I want you to run that on these 10 samples, and it's pretty hopefully plug and play for them. Right? Okay, that's your question.
Yes.
Cool.
So email TA support for that.
Yeah.
Okay.
And if they're being annoying, come ask me and I can track down the right person. But that one should be like a really easy answer for them. That's not like complex.
You
It's like
think.
No. Reversing heat capacity is actually a very complex thing. The basics of like how you test the viscosity, if the Rheometer applications can't tell you that, let me know. That's a problem. Reversing capacity is really tough. I can give them some leeway if they should, but
Okay.
you know what I mean. It's if they can't, that's a real problem. But yeah, that's your basic running. Any other questions about it? I hope that like kind of put a lot of what I was saying kind of into context of how it works and everything. Any other questions there? All right. In that case, let's clean it and let's get your accessory set up.
Okay. Are we gonna try the impedance?
Yes, that's what we're going to get yours set up and run that.
Maybe we can run your aerosol sample. You have the nanoparticles inside the.
So just
ink?
leave it up.
Yep, move it up.
Oh,
Again, if you
so
had a
another
thicker
part-
sample that was, Kim wipes acetone.
I'm going to use white paper towel. I can wipe it with paper towel.
Yeah. I would do it like dry first to get a bunch of the excess up, and then use acetone.
Yeah.
You have acetone.
So yeah, this is literally the material. It's like a silver nanoparticle ink material it's conductive ink.
I make no promises,
Yeah.
but we can try it.
Yeah, that is.
I will go ahead and preface everything we're about to do with, I've actually never set the successor up before, because we don't have many of them out in the wild. My knowledge of the underlying science is fairly limited, but I can walk you through the steps, get it set up, and we can work from there. This one's going to be one where I might have more, I'm not totally sure on the answer to that question to give you guys. And I apologize for that, but I'm not.
You're pretty good.
I'm the
Yeah, you're also pretty good. Yeah, I just want to tell you, this is kind of viscous.
Yeah, that's the thing. It's not very thick. I think that might
Yeah,
pose a problem. We might have to play with that a little bit.
Yeah, it's pretty thin. I would say.
Yeah.
Might also we need some acetone to clean it after measurement because
Yes.
Can you
it's
shake
used.
it?
Yeah, we.
Yeah. We'll shake it before we put it on for sure.
So this is, you only have one,
Uh, yeah, we have two different bottles.
Okay, which one is it?
Similar.
Similar.
That one is a little bit thicker. Maybe that one. This one is like
I just
5
remove this thing?
Yes.
5 to
Remove
10
it.
CP.
Make sure
Yeah.
before you start doing this, make sure your gloves are clean.
Oh.
Yeah, you don't want, like, you have a bunch of junk on there, you don't want to start playing with the top of the bearing and then get stuff into the bearing because it falls off of your gloves. So do keep a conscious mind when you start playing with the fixtures and things of your gloves, especially as you come over to the computer, because if your gloves are covered in lovely ink and you start playing on the computer, and it's conductive ink too, it might not end up very, very good. Just put it back. Awesome. So. Yeah, putting a trash can here would be very helpful. Okay, so this is our impedance accessory. So you've got your lower fixture, which I'm going to set this up for you guys, but you got your lower fixture, so this will plug into these cables that you've been seeing sitting here. We have our upper fixture, this is on the top, and then we have our lovely cables, our actual OCR meter over here. So, first, I'm going to just pop this. Actually, I'll plug it before I do that. So,
Are they color coded?
yeah, luckily.
To those two?
So this is labeled. It's not color, but HPOT, like they're all match, and then you
Oh.
just check the color. It's like black is going to go to L curve. Red is going to go to pot. Blue is going to go to. And then that also. Setting this up real quick. I'm gonna actually cool this down a little bit. I'm gonna take it to 15. Just maybe that'll hopefully thicken up the ink a little bit. We're gonna see. So keep in mind here too, when we put this on, there's a lot of thermal mass here. You're gonna want to give this a good amount of time to equilibrate because the temperature controls here. It's gonna go all the way through that plate, right? So you're gonna want to give it a good amount of time whenever you install this to go. But you put it on, there's little locks, you just twist it right into place. Then each one of these leads is color coded.
So this one just go with our. Look at this thing. Why we need to add up this one instead of just measure on top?
It's impedance.
Because impedance.
Okay.
So this is, give me 1 second. These are like not hard, but you have to get them pretty well lined up. So what you have here is two conductive surfaces with an insulator in between, and their material spans the distance. We're going to measure the impedance through it while we change temperature or we change the rate, so we can see how the impact of that impedance to the viscosity. Or, yeah, in this case, it's flow, so it's pretty much going to be expressed in viscosity.
It's just a little clip.
It's not a clip; they're actually little pins. So the whole,
I just pin
yeah, it's kind of squeeze them out. And it seems like it should be easy, but I found that they're actually a little tougher to like get lined up than you'd imagine. They're not like impossible. It just you got to be pretty precise. They're like very well machined. That's why you pay so much.
it. I know.
So all that's color coded. From there, I'm gonna turn it on. There's a switch on the back, and then there's a button on the front. You can just use the button on the front. I just turned it off last night, so it takes no extra work. Cool. From there, we're going to install our upper geometry. Pretty much in business. Oh, it really helps when it's trying to cool if you have the chiller going. Otherwise, it's going to start getting warm. But it's got to wick that heat away, right? When it's cooling, especially, it takes some time. But now it's going a lot faster. So make sure this is running. So now we're pretty much up. The first thing we're going to want to do, it's going to sound louder because that bath heated, and now it's got to cool down. So we need to actually calibrate this, both with everything that you saw us do on the other one. So we're going to bring it down, zero the gap, do the inertia, do all that, do the instrument inertia if needed, if it's been a while, but since we just did that, we should be fine on that. We just need the geometry. And then we also need to calibrate the fixture here with the impedance module. All right, so there's an extra layer of calibrations. And that's really easy. We have a set of shortening strips. Which I tucked away in here. There's like little metal pieces. Only touch these with gloves to prevent corrosion on them. As you're building up oils, will corrode, and then they don't work anymore. They're just conductive strips. And basically, we'll short it with those, and then we will leave it open as well to check basically zero and short, and then from there we're good to go with the calibrations. So to begin with, we're just going to do the geometry calibrations while everything kind of equilibrates over there. So this one, if you notice, actually has a barcode on it. So by comparison to mine, which is the older design for our old system, this one has a barcode. Mine has a magnetic strip. So this machine can't read mine. That's okay. Any ones you buy now will have the barcode. And there's a reader in there for that. So when you're using your actual geometry, you'll have Smart Swap toggled on. So that's this little button right here. And it'll basically read it and then tell it what is attached. So if you want to put that back on. Cool. Well, I'll just toggle Smart Swap. It'll say, hey, are you ready? I'm going to go ahead and read it. In your normal operation, if you're flipping out, it'll just stay on, and as it flips, it'll automatically read it. But because I have to turn it on,
What did you flip?
toggle Smart Swap.
Oh, that's okay.
Yeah, before it had no check. Now it does. It's active. It'll read it, and then you should see, like if I hover over this, it'll tell me, hey, we have the Rheo impedance accessory. So it knows what it is now. The next step, what we can go ahead and do, is get to the actual LCR meter connected into Trios. So to do that, we need to know what COM port it is. This is you're gonna want to write this one down. So we're gonna go to the device manager. Then we will go to this ports section right here. And in here, you'll see this USB serial device. The other trick for this, if you unplug it, you should see it go away. There's no more ports. If I plug it in, of course it's the only one you have anyway, but
Device manager.
yeah, it'll be there. That tells us it's COM3. So now we know. And if you leave it in the same port, it should stay COM3 unless you reassign this to a different port, which you can do also in the device manager. Don't do that. It'll say to COM3, but this is how you check it. If, I don't know, you get a new computer, you get a new device, whatever, this is how you set it.
What's this for?
The LCR meter. So it's actually plugged into the laptop, so that way it can read into Trios.
Oh, so USB.
Yes, yep. So, it's COM3.
One thing, go do it again. Oh, okay, on the computer device manager.
Yeah, it's
Okay.
computer device manager, yes, sorry. So, we know it's COM3. We'll then go into the little icon up here. We will go into Options. We will go to Discovery HR. And because you have the LCR meter, you'll see that option down here. So you'll click on it. You'll see it says, there's nothing currently connected. We'll go select COM3, which is also your only option. The baud rate's fine, and it'll just say connect. When it's connected properly, you'll see this LCR meter go to enabled. So if I disconnect it again, you won't see it. But once it's connected and it sees it, you'll see that enable option show up at the bottom.
Okay. 1 second.
Done.
Use, option.
You know what the solvent is for the.
Generally, when you leave after you made an adjustment, make sure you hit OK. This one, since it's just connecting, it's fine. But if you're like changing settings and you hit cancel, it won't save that.
I'm not sure what.
And then it'll, it's gonna hit OK. You gotta give it like 30 seconds to give its life in order. So that's that. So now what we're gonna go ahead and do is calibrate the actual geometry.
How is this looking?
Yep, same exact thing. Nothing changes. I will point out, because we are sub-ambient now, you're gonna see some moisture buildup on the top of this plate. Keep that in mind. It's just gonna be a reality of what you're working on. If you have less humidity in the room, you'll have less problems, but more is what it is.
Wait a second, what is this? Is this a paper?
It's an insulated material.
Oh, it's
So you have basically two
It just looks
connectors.
Because I didn't use this settings.
Yeah,
Are you gonna how much material are you gonna use in this area?
enough to fill the space between the plates.
So
I don't know how much
Is
that's
it
gonna
higher
do.
area or this
I mean,
oh this one.
yeah. I mean, we'll have to use a little bit more, right? Because it's going to flow out and everything. So, inertia, friction.
1 second.
Thank you.
Get an arm workout in today.
Yeah.
Get a 10 gigabyte video at the end of it.
Yeah, it's already like an hour right now. You should be doing this. I don't like how all you're on like 6 feet. See, I don't like how all y'all tall. Look at that. Y'all can see eye to eye with each
So
other.
may I ask, are we trying to measure the impedance as a function of viscosity?
Well,
Yes.
So literally means that because this material, when viscosity change, we want to measure its impedance.
Yeah, basically. Well, not necessarily. I mean, yes, it's a function of viscosity, so you could do it at a constant flow rate to measure.
Or ramp at different temperature, and then we measure the impedance, or in other words, the resistance.
Yeah.
Because this material is the best of my knowledge. Sorry, this material. So its resistance increase as a function of temperature.
Sure. Yeah, you measure it.
Yeah, but the thing
In the
is-
viscosity as well.
Yeah, the thing is that normally I measure the resistance after I print it out and sinterate it in a solid form. Then I measure. I don't know how do I dare use it in liquid form.
Yeah, I mean, it's
We're gonna
gonna.
try and see it.
What you could do is, because you seem that 100,
Yeah, more than 100, 100.
yeah, so you could potentially,
Oh,
yeah, but not today, but I guess, just
yeah.
get it out afterwards.
Yeah,
See
but-
how it changes. And then we'll stick to it.
It will be solidified. The solvent will be removed and become
This is no
solid.
disposable.
They're not disposable, no. I don't know that they exist for this, so make sure when you put on here you have a way to get off of here.
Yeah,
It's gonna be cured.
That's the thing I put it here. The alcohol.
Yeah, IPA.
IPA or
Yeah. And that's the case, you're fine. The big thing is when you're done with it, if it is like completely solidified and the plates are kind of stuck together, you'd want to like loosen and remove this and then send it up and then take it off. That way you don't mess up the bearing in the process. Because like, if you mess with these, that really stinks and it's not super cheap. If you mess with the bearing, it's $20,000 to $30,000. That's a very different ballpark.
So let's say if we want to
Well-
clean the whole thing, we can unscrew those wires, right?
I don't know that you unscrew them. You probably disconnect them and then clean it. I don't know that there's a way to. I mean, I guess there is, so you could. Yeah.
Actually.
Yeah. I mean, it's there. You just got to put it back together carefully. Make sure you don't mix up where it is and everything.
Looks like it's metal, ceramic.
Yeah. It's. I don't know that I would pull off T screws because the whole thing goes together. But like the screws for the wires, you get them out of the way. Yeah. Then you just have to make sure you put the red and the black and the white where they are supposed to be. Otherwise, you're gonna start to have a lot of fun. Take a picture.
That's in the future.
All right, so rotational mapping's done. So now we need to calibrate the impedance side of this. So if we go back into our calibration screen, and then we go to the accessories options in here, the only one that's going to exist here is the dielectric here. So we're going to use the calibration wizard, and we'll hit calibrate. So it's going to say, hey, make sure that it's installed. And actually, I guess a better way to start this, we should zero the gap first. It'll do it again, but it's a good idea to go ahead and have it done.
So finish the.
Finish all of
accessory
your
side.
other ones. Now we're just going to go and zero that again.
But then, you can move.
Yeah, it'll actually re-zero it too as a part of the calibration wizard. But before it starts, it's nice to give it some idea of where it is. And we'll set it to a millimeter. That's what the manual stipulates. I don't know that you'll have massive issues if you don't, but when I follow a manual, I read when I try to follow it.
Okay, so you calibrated temperature, equilibrium, and zero it.
Yep, zeroed it. So now, effectively, if we weren't doing the impedance side of this, the machine's ready to rock. Like, if we just wanted to use this as a stage, we could, right? So, from there, back here, you're going to set this to be 1,000 real quick. The millimeter is just what the manual says to put that, so we'll do that for the start of this calibration sequence. So, you weren't here for this, but you go to calibration, you go to accessories, and then you'll see this screen. All right, we're going to use the calibration wizard, and so it's going to step us through the process of zeroing the LCR meter. So it's just going to tell you, hey, make sure everything's connected. If you try and start it and it's not going to work out well for you. So calibration wizard, we'll hit calibrate. It'll go ahead and you see it's going to zero that gap for us again, but yeah.
You said this gap is 100 micron?
It'll go to it. It'll zero first. But now it's going to step pretty far away because it's going to do its next. It's going to do an open circuit check.
Why
The machine's automatic doing all of this. This is all under the hood. You're not doing anything. So now it's performing the open measurement. So you'll see on the LCR meter that now it's adjusted for that open. So basically it's zero, so it knows, hey, we're not touching, we're not connecting your to anode electrode, or electrodes. That's a term one. That's English. Yeah.
So your plate is 47 micron, and ours is 100.
It'll be 1,000.
That's not 1,000.
Yeah, because it's a parallel plate. I don't know if they make cones that work with this or not. I'd be interested for like lower viscosity stuff, but
Does you have a kind of insulated?
yeah. But it might be because the distance is shorter. If it were to be, that could be a problem or something. I don't know. So cool. That open calibration is done. Now it's going to tell us to place the shortening strip on it. So those strips we had here, I'm going to have you do this because you have gloves on. You're just going to place the strip across, like connecting the two parts that stick out, right? Lengthwise. Remember, we're not touching these with bare hands. It's only gloves, just to protect the material. Mm-hmm. Yep, that should be good. From there, we hit continue.
What is this?
Short.
It's just like a metal braided material, conductive.
What is that for?
It'll shorten out the electrodes. So it'll basically be like a fully complete circuit versus a completely open circuit. That way it kind of makes its balance.
For impedance calibration.
So it'll come down, it's going to apply force, so it'll get to 50 newtons here on the head. It'll manage that itself, so you can see it's squishing the...
What do? You just
I just hit continue. It does that itself. You just put it in the right place and hit continue. It'll bring it down, go to 50 newtons, and then start this. That way it makes sure that it has good contact across that. And then you'll start to see this say, I'm adjusting now, the LCR meter is calibrating.
I guess this thing should last a while and break it or.
Yeah, I mean, as long as you're being careful, you can reuse them. They're not like well, they are eventually disposable, but they're reusable until like you see them be really corroded. Because once you have a bunch of corrosion on there, it's not going to work as a shortening strip anymore, right? So that's why you only touch them with gloves, that way you don't get any oils on there corroding them or anything like that. Try and keep them in like a dry place, as dry as you can anyway. Cool, so that's done. So it's going to say, hey, you can repeat that calibration if you want, if it for some reason fails. Like, let's say it didn't make good contact or something like that, or it's too corroded, and so it can't get a good measurement or something, it might fail. Ours passed, you got a check mark. So we're good there. We just have to say continue, and it's going to finish that. It's going to actually go up first. Then we're going to do a confidence check. So it's just going to double check that's right. So basically check the 0 point. So you can pull the shortening strip in just a second. We can remove it. Again, I'm just following all the instructions right here. From there, they just hit continue, and it's going to do the confidence check. Or does it actually go down for this? Oh, just a millimeter. I'm pretty sure this is just checking the 0 to make sure that it actually is effectively reading 0. We are moving to the point of which I don't know nearly as much about what's happening with the impedance meter. I will admit, I only know it so much. Yeah, well, and it's not common, and it's not good. So that actually failed on its capacitance check. So we want to rerun that, right? We got next. Rerun it.
Rerun the short.
Just top to bottom. Since it finished out and it didn't pass the confidence, we're gonna have to restart it in the calibration wizard. Don't touch it. It's zeroing the gap. You gotta completely restart the calibration wizard.
So you just start you click calibrate, it's going to zero it out and leave it up.
Yep. Basically, it does all those first steps instantly. And I wonder if it's actually the moisture buildup on the top of that, from it being subambient right now, causing an issue. Which means we might have to increase the temperature to do it again. That's not supposed to go on yet. It's doing the open measurement still. We're just going to go ahead and cancel this real quick. This is going to be a problem. I'll just hopefully let it finish. So don't get ahead of it. Make sure you're reading when you're doing it.
Have this up as a
Sound juicy.
I don't think
Is that my cue?
It just failed, probably because we put the shortening strip on top of it during it, so it like. That's gonna be
Let's restart it.
yeah. Well, I'm gonna cancel to go down. What I'm gonna do is also heat it up, just take that moisture off of it. Yeah, well, first it's zeroing the gap, then it's going to go do the open calibration 0 point, and then it'll do the short, and then we do the confidence check. It worked yesterday, so I know it's not broken. Something's up. Don't break stuff.
So, if, you know, after you finish this training, if in the next couple of weeks, if you have a question, you may also have option to bring you back up to.
Not to bring me back. No, I can answer questions. If you want somebody else to come out from my Gaps team and talk to you about it, that's something that you can pay for. But this is pretty much it. Now, if the machine like breaks, it's under warranty and everything like that. But for just specific training, no. That's no. Now, if I'm happening in the area, or if Jose is your actual technician, I'm just helping out. I'm based in Richmond. Your actual guys are Delaware-based technician. You know, if we're free, we generally will, agree to stop by and do a courtesy visit or something like that. But
The nearest one is Delaware.
I think I might be slightly closer. If you put it on the map and drew a line, like I think I am closer. But I'm not your technician. I know that might not make sense, but it's true.
So, what's his name?
Jose.
Jose. So Jose is my point of contact for this.
Yeah, he's your main service guy. You can, like, I still exist. You can reach out to me. It's not like I'm gonna. No, don't talk to me.
So you're in Pittsburgh?
No, I'm based in Richmond. I'm going to Pittsburgh for my next job.
Okay.
That tip of West Virginia is my territory.
So which one is
Yeah, but he's based out of Wilmington, Delaware. So he's kind of like almost the same distance, the opposite direction as me. But with 95 traffic, like it might be closer, but it's probably not faster.
Alright, now it's
Yep. So now you put the shortening strip on. But yeah, when you have like big service things, so they be the right person, you reach out to me. I will put him on the email if like, you forget or something like that, and try and answer it or pass it to him. But he would be the actual person that like it comes down to. He's responsible to come out. If I'm free, I'll help him out. DC, because it's kind of in between us, is a pretty easy one for me, especially because I drive by to go to West Virginia fairly frequently. So that doesn't matter. You might see me, you might not. I'm just giving you that warning. You guys are kind of in between the two. So, and Blake is like just outside of Baltimore, so he is close, but he only does the DSC for you guys.
Oh, he's in Baltimore.
Yeah, I think he's a little bit outside, like towards Delaware. But yeah,
Okay, good to know that.
that's concerning. Yeah, I mean but he also so the difference between Jose and Blake is they have it's like my secondary product line, so I cover Rheometer, I cover TGAs, DSCs, all that. So my territory, since it's kind of our bigger product lines, is smaller. I just cover Virginia and West Virginia. They have DSC and Rheometry, so Jose does the Rheometry, and then Blake does the thermal side, the TGAs, DSCs. But they both have smaller secondary products that they cover like the entire southeast. So they have smaller regions of one single product, and then they ship out much further for their other like less like you know the guys that work for DLF. Your guys in Ohio, and he just covers the southeast.
Oh, the girl who helped me is definitely in headquarters.
Yeah, that she's the technical specialist in house. But if that breaks, she won't show up.
Hopefully it didn't break.
Huh? I'm just saying, like, if something were to go wrong, you would need Anthony Tata, who now Antonio came out for this one. He's based in Ohio and Columbus. So the smaller products, like we don't sell as many. There's one guy, bigger area.
Press repeat to repeat the short calibration or press continue to finish.
So pass so far, so you just say continue. If something were to have failed, you would repeat the short.
So this is the well we filled last time.
Yes. Now you can remove the strip.
Pass.
Yeah, moisture.
Okay. So you increase temperature to
30, that way you're going to drive off any moisture, and dried it too.
humid.
Yeah, not exactly surprising. Water's not good with electronics. You know.
That sounds good.
Yeah. And it only failed on one of them. That's why I was like, there's something here. It's not like a complete issue. And give me 1 second. I gotta take this call. So, now we set up this experiment. I don't know what this is called. For now. What is there better?
It's a fine.
So the big difference here is we have a new step option. So complete everything here. Add one. We're going to have this Rheo impedance flow. So with this particular accessory, it's designed to operate just in flow mode, so it's just going to spin. We're not going to be doing any oscillation stuff, just pure going around. That's what it's designed for. Yeah.
So for this setup, we can only choose this reinvented flow.
Yes. Yep. You won't see an oscillatory or anything like that. I mean, you could run an oscillatory test on these fixtures. Like that's going to be fine. It's just, why would you?
Okay.
Right? I mean, you have it all hooked up. You wouldn't do that. You would only do it,
Okay.
no point in getting that fixture dirty when you can just get the plate, which is easier to clean. Just like the other one, we have other options. So you have sweep, you have peak hold. So like you could change the rate that you're doing with an impedance going through the material, everything's like that. We're just going to do peak hold. Keep it simple. We are going to. I actually was curious here earlier. Let's just see if Express, if this still exists. It does. Okay. I don't know that it changed anything much, but you know it's there. We will again just do 1 rad per second. Go kind of slow with it. Minimum sample, so that's fair. It's, we can step it down. Let's do 15, just because it is 600 seconds now. It's 5 minutes.
Oh,
And then you can set your voltage, and you can sweep. So like you'd be keeping this constant, and now you're changing that voltage applied, right? You only can change one thing at a time. You're not going to change two because that's self-explanatory. That's like 3rd grade stuff. But I have not played with it at all, so I don't really know. We're just gonna use these defaults and see what happens. Maybe we don't go all the way to the peak. Let's just do to like 250.
So what are you changing? You're changing
The dielectric frequency that it's doing, and we could change the voltage, but I'm gonna keep it low at 0.1 volts. I'm not gonna go too crazy. Honestly, let's do like 10 to 100. Let's keep it at pretty low. You can do different ones, so you can do like a discrete to where like you're doing multiple steps, or if you just wanted to do like keep it constant and just do one measurement at one everything, you do that. You can do linear or log. It's just how many points it's going to put in those regions. And we'll do 10 per decade. You guys have the Hioki LCR. We have a different version of it that you have as well, but that's explanatory. Slower is the average time, I guess, between points. We'll leave it at slower. And it's in series, not in parallel for your equivalent circuit, which is how I guess it's gonna do math. Sounds good to me. I have no promises on that it will turn out to anything, but hey, we can run it. So if you want to go ahead and load the sample on, I would shake it up first, because I assume that ink settles out a little bit. Yep.
Stronger.
Yeah.
You got it. Come on. You. Yes,
Yeah,
that's the
go.
point.
Maybe I'll be gone. This
5 pen.
Foamed up. Yeah, it's pretty thin. We're gonna see how this is gonna work.
Kevin, you should use it from the bottom too much. Stick all the way to the bottom of the bottom.
Yeah, just trying to avoid some. You might need to like push the eyedropper.
Yeah, well,
It's very watery.
Yeah, we're gonna have fun because it's a parallel plate too because of that. So don't worry. I would put. Yeah. You have a paper towel next to you. So obviously don't want to short it on the side. So try and clean that bit off the stage too. On the bottom. No, I meant up here. There matters too, but I'm really concerned about that area.
See how great it changed?
Because like we don't want to connect that insulator on the side. We just want it to be connected. And you might need to use some IPA to clean that. I'd probably just put the bottle down for now. Yeah, wipe as much as you can, and then use the IPA to just clean off that side. Because I don't want it to connect like the insulator over here, and then our data's all funked up. Yeah, it's okay if you pull some of it off in this situation. And it's ink, so we're gonna have fun cleaning. He was saying IPA. You have the other bottle next to you.
it's recording now. I can't tell
We
you
have
what I want it to
acetone
be.
too.
Give it a moment. I know. I got
But
you.
yeah, just I clean that head over there.
I hope this ink will not contaminate it. Sometimes I feel it's not really easy to remove it. Also, mask, are you running at a low temperature, like 25, or are you trying to run high temperature?
It's at 30 right now.
30? Are you gonna ramp up to a high temperature for the measurement?
I mean, we could.
Yeah, because one thing for this ink, I mean, once you're reaching like 60 degree, 80 degrees, starts to solidify. So you
We won't be there. We're not gonna. And when you guys are testing this, of course, you'll know, like, hey, we probably don't want to solidify the material between our plates. You probably shouldn't do that.
It is, yeah. Otherwise, the data will just messed up.
Yeah.
Is that a perfect demo of what happens if you too much fluidic? You use asphalt?
Yeah, Aston or Apple. Yeah.
What's the manufacturer's size?
These should be 35 CP, I guess. 25 to 35.
That is a low CP.
You can double check.
So 50% of the money.
And I value my phone more than your life. I shouldn't say that right now.
Seems pretty good. You're gonna get it. You know, there's only so much you can do.
I mean, we're gonna do it one more time afterwards, you know.
Well, you're probably gonna do it a lot more times after this, I imagine, given that now you have the instrument.
Yeah.
We're gonna put a little
Okay.
more.
Thank you.
Because I think instructing is a bad idea to use the ink.
You gotta do it once to learn.
Yeah.
I would recommend, what are we? Gas cutout. Gonna go, that regulator probably needs to be replaced.
Alright.
Or just a completely checked top to bottom. I don't know. There's a leak somewhere in it. I don't know where it is. You can hear it.
May I ask why there's a spill we have to deal with that gas?
Huh?
I mean, we saw a spill. I thought that's the problem. Why do we have to deal with the
It just also happened to go out at the same time. The tank was low when I came in this morning.
Oh.
Because it's not this machine, I don't think. I'm pretty sure that, like, if you walk up to that regulator, you can hear it.
Oh.
I don't know where the leak is. I put new Teflon tape everywhere, but I don't have a leak testing solution with me.
Yeah.
So somebody's gonna have to sit there and go around and figure out where that leak
So then,
is.
if this is leaking, which means that the force to pour this to
If
dry
that's
it-
leaking, it doesn't matter. As long as the pressure of that regulator is what it needs to be, this will work. It's just gonna be draining the tank faster. That's all that it is. Once this doesn't have pressure, it'll tell you. And you saw it. It
Yeah.
gave you a little error. It showed up on the screen. It said bearing pressure low.
See, that's 20 PSI.
I'm sorry?
This one is 20.
30 psi. 30 psi. And when you do get that, be very, very careful. Do not touch this bearing when there is no air going to it. Don't look at the machine. It doesn't exist anymore. Go fix that.
Otherwise they'll free form or something.
Well, it already has. And so if you start messing with it, you'll actually be messing up the bearing potentially, the carbon plates in it, and maybe the encoder it is. So when the air shuts off and the bearing stops like that, do not touch this. Fix that. So I just moved it over to the regular. And what was your?
These conductive sleeves here,
Yeah.
you have to use specialized ones from the company, or as long as it's like not corroded, you can use it.
I'll be honest, you'd probably get away with it. You have to try it. I'm not gonna make you a promise that it could work, but you could probably get away with it if you just had like a conductive copper strip or something like that. Would be my guess. Ideally, of course, the TA message is no, buy them from us.
Exactly.
But so I didn't say this. That's not on recording. But you could probably get away with it. I'll be honest. Yeah, I'm also sure if you asked me, I'd probably, like, assuming the part numbers, it probably is not expensive, and I would just ship them to you and not care. Something like that isn't super stressful. When we started talking about pans and stuff, that changes the game a little bit. All right. Cool. So, we got that loaded. We're gonna have some fun. So now you're gonna send us the geometry gap. We're gonna see how this works. You might need to add some more, and we'll spin it. So we'll let that go. We're gonna go here. Nope. We're gonna just start spinning it. and I'm gonna have you just take your pipette and just put a little bit on the edge. The hope there is that it'll kind of stick between the two surfaces and stay in place, make a nice drop. We're gonna find out what the contact angle of this is. That's what's happening here. And if it beads well or not. And worst comes to worst, we can lower the gap size.
Like this?
Yep, exactly. And then just gently deposit it. And then the hope is that it will kind of fill up that gap. We're going to see how that hope goes. You can put some more. There's still a good gap over here.
I have to say it's more
1 millimeter is very big gap.
Yeah, it seems really small, doesn't it? Until you have a really not viscous solution. And you can lower that, right? Like if you guys decide we're just going to always test at 200, I mean, it's probably pretty fine. I don't know how much that will change your measurement. That's not a good question for me. But if you guys are doing it consistently, like we said before, consistency beats almost anything. If you do it consistently wrong, you can still get something out of the data. If you do it inconsistently, now it's all useless. So, there you go. And it looks pretty filled. You know, as long as we're going to get it, I don't think we're going to get much better, right? So, from there, I'm using my cart. Below, there it is. Trim it. I'd put another glove on first.
This is going to be colored up.
Well, we use that, it'll be fine. It'll be fine. It'll be fine. If it's not fine, I'll beg the guys in house to send me out one. Or steal a hotel key card tonight and cut it.
I like
What are they gonna do about it?
There you go. A question for them: if we decide to do something else, do they have to be at those dimensions for those?
I'd imagine not. I think the idea there is that it can crush it and push it into place. So as long as it's something that's kind of thick, I think you'd be okay. I haven't tried it, so I could not tell you yes or no. My thought is it just needs to short out the plates. Shorting out the plates, you should be okay.
All right.
Now, I might be wrong about that. The machine will tell you that. But yeah.
All right.
Okay, I'm going to check the water. It's very liquidish.
Yeah, that's how it happens, right? So, from there, we're just going to hit start and hope that goes well. And hopefully not send ink flying. You know? Yeah, okay. You'd have to be going really fast. We're going 1 rad per second. It can go to like 300 though, and then it's just it'll send stuff everywhere.
I was wondering.
Let's do that.
Do you want?
I don't want to
these
ruin.
on?
Oh yes, you should. You're
I mean,
right.
that's why not.
Yeah, no, you should put these on. I
I used to
apologize
already
for that.
print some, yeah.
Yeah, you would just. I'm not gonna mess with it now and undo this because I don't want to reload this sample. It's kind of tough. But I'll show you guys in a second. Yes, you would put this on. It keeps the temperature more consistent inside of the system. Pretend that's there. All right. I'll show you how to set it up in a second, but I'm not gonna undo what we have here. This is a demo. You can visualize, imagine.
Filming everybody.
I was just wondering when the data's coming. The training?
Yes.
I hope the try this gun into everything. Because like I said, I have to get on the road and drive 3 to 4 hours after this, so. Busy day. We did the best we could. 1 millimeter's tough for this spin of the sample. So you might have to either adjust it down or keep doing it if this is what you're testing all the time. But that's what I was looking for.
It's about 10 to 20 cp.
Well, so we're gonna do viscosity, but I was also curious if it plots impedance from this. I don't know how to get that up or how it works. Or if it's just if this applies it and then we're just measuring the viscosity result of it. That's probably what it is. I was assuming though that because it plugged in, maybe it plots the data that comes off of here, and so you can see like but I guess not. So that might be something I can check.
90 ohms.
Yeah.
97.
Hey, makes sense.
Yeah, it was manual before you now it's
I'm gonna do a bit of paperwork real quick.
you got some resistance is that?
Resistance?
Electrical resistance.
Oh, okay.
This one's for liquid. This one is liquid. Is this only for liquid?
They don't want to
Is it only for liquid?
They don't have they only have the resistivity and the solid form.
I don't. I'm assuming it's better.
You can treat just as silver maybe. I don't remember. Yeah, I'm not quite sure.
Well, I just imagine that once it's solid, that resistance is
So
better.
once it's cured at 120 degrees C, that's the resistivity over here.
So the resistivity. Yeah.
Yeah, and if it's thinner and higher temperatures, you can see the resistance
Yeah.
getting lower.
Yeah, that makes sense.
You can just use it.
Well, I don't know how relevant it's going to be here because it's still in suspension. Like once it's solid, it should be much more. I mean, you would imagine it's much more
Yeah.
conductive.
But the idea of this ink is supposed to replace the bark silver. So the resistivity typically the literature says that it's about 1/6 of bark silver.
Okay, I don't. That doesn't mean a lot to me. I'm gonna be honest with you.
So you can just use this number just for reference now, right?
Yeah.
So this is enough. It's better than nothing.
Actually plotting. See, once you start plotting, you got a lot more signals.
I didn't see her after.
It's been doing that. I played this. I got no idea. And then, I mean, maybe we do it as a function of time. Curious.
What is that?
I'm assuming these are all different impedance or the dielectric frequencies. So yeah, you can see each one of the. So we did frequencies with different steps, and then it's just plotting them, and then you're seeing. I mean, in this case, times you're seeing the conductivity across it. I don't know what that actually means as a function of anything, but I'm sorry, I'm not super helpful. There is a lot going on right now. But yeah, so you go into like variables like you do on the DSC, and then you can set whatever, like, what are you interested in. And the second that like it started plotting, it just populated with all of this. So you will have the data that comes off of that. I was wondering how that happens. And when you're seeing that resistance really change.
Is that because of the?
I assume it's the frequency that it's plotting value really. Because everything else in terms of viscosity, like the temperature, the rate are all the same.
We have to.
And I mean, in fairness, it does look like there is a change depending on the frequency, and it's uniform across each one.
This ink do come out, right?
Do what? What do we see?
Ah, dude,
Conductivity.
I just plotted against time, so you're just seeing for like the runtime and then each of the different frequency sweeps that it does.
Yeah.
And that's across the meter. So you're just seeing it plot. I mean, it looks like there's actually something happening. I don't know what it
Something
means.
happening, like I can feel like in this specific cycle the
And we can also change
this is
that.
conductivity. So
Yeah.
resistivity decreased.
Well, here you can actually just plot resistivity.
Yeah, resistivity. That's easier to more straightforward. When resistivity increased with higher frequency, that's what we get.
And we can also put it into the right unit. So when you come in here, hopefully resistivity is an option. I do hope. It might not be. It is not.
Oh, it's
I lied.
fine. We can see the thing. It's okay. Resistivity decrease.
Yeah, it
with
might also be
increase.
easier to kind of look at it like this. Well, it's doing them so fast now.
What is the sweeping frequency from 1 hertz to 1,000?
10 to 100.
10 to 100. Okay.
Yeah, it can only do 4 to like 800,000 or something. I've
At
seen
least
like
we're
that.
seeing it's changing, and it looks like it's pretty repeatable, relatively repeatable.
Yeah, it does.
Yeah.
So it's like there's something happening. I
So
don't.
Is that increase from 10 to 100, 100 back to 10?
It's gonna go to 10 to 100.
10 to 100 all the time.
Yeah. That's just because that's what if you set it to be in here in the experiment, if you set it to be 100 to 10, but it's gonna start at 10 and go to 100.
Okay. And current voltage is 0.1. Yeah, it's hard to tell. It's my first time to do this.
No, I know, but you're gonna have to.
Normally, what I deal with this thing is I print it out. There's a technique called isojet printing.
Yeah.
And then I sinter it, solidify it, and then use multimeter to measure its resistivity instead of using this impedance.
Yeah.
Because I'm wondering like why people wants to learn the resistivity in the liquid form. Because what I'm doing is I'm literally printing some cable. I mean, just thinner than this using my technique.
Yeah.
But this tool is measuring the resistivity in the liquid form. Like I was wondering what scenario people is applying this technique to. Do you have, okay. Yeah, I'm just thinking.
I'll be honest. No, I'm not really sure. I can ask somebody and find out for
Okay,
you.
I'll learn
But I'm
more.
assuming because like it's partially supposed to test dielectrics, and some dielectrics are like a gel
Okay,
or a liquid
yeah,
state.
yeah, exactly.
So I would imagine that's why.
Mhm.
Is their material when it's actually in whatever their system is a liquid, and so
Yeah.
they want to know. It's probably not so much for slurries like this. It's for if you have one of those
Yeah.
like gel dielectrics or something like that. Would be my.
Yeah. By the way, I
Humble
think
guess.
if we have a gel material, it's just easier for this training.
Oh yeah, if you have a gel, this is a super easy test. You just need to
Right.
figure out what you're doing over here. But like, dummy,
Just-
easy to set it up. It's just the liquid with the parallel plate is.
Yeah, just because our
Really
PI indicated, that's why we want to try this. Otherwise, I know it's because one important thing I don't want to run it here because it's not easy to clean it. This thing
Yeah.
is
Yeah.
pretty dirty,
No, that's valid.
Yeah, but it's doing something. I can see from the plot.
I just don't know if it's meaningful something, but it's something.
We can read some literature and learn what does it mean. But I can see some resistivity. No, we are changing shear rate. The shear faster restore, then the resistivity kind of increase.
Actually, the shear rate's constant on this. It's the frequency here of the signal that it's sending in.
Oh, it's that frequency. It's not
Yeah.
like the reverse.
No, you could do that too. I just made it easy and was like, we'll just play with this.
Then what changed that?
The dielectric frequency.
Dielectric frequency changed.
Yes.
Increase. That's dielectric. Sorry.
You can do it the way that you're saying though. 100% something you can set up. I just was like,
Yeah.
we're gonna do something and
We don't want it to fly. I know.
yeah, we gotta crawl a little bit first. Maybe roll over once or twice. Try not to
You
hit
know
our
what?
heads
Be a
on things.
disaster. I would not suggest you let it fly.
Yes.
Well, I am more.
Yeah. And also maybe we can just close it.
I'll suggest
We don't
you
need
to
to.
fly.
Yes. I'm sorry.
I'll suggest you to fly.
We don't need to paint the room.
Yeah, because this probably.
It come out, right? I can completely wipe it off.
You can. You just apply more. You can eventually. I mean, just slowly. That's why I don't suggest it. It's not like the gel material, like it's soluble to water. Put
Yeah.
some water, apply it easy, 1 or 2 moves. But this thing is more difficult.
That's gonna be a work in the next hour.
What? What's going to be more?
Wipe it off.
It's
You're
being
so welcome.
it's being recorded, so I can't tell you what I'm going to tell you.
It's okay.
You can say no.
Huh?
You can say no.
Yeah, just wait until the recording's over.
Okay.
You know, yes or no, or maybe you're not gonna do it.
Mm,
But anyway, that's pretty much everything with the system. I guess you guys have any other questions, comments, concerns, worries, fears?
you don't have time for fears. So what's the coolant for this one?
It goes over here. It goes into the Peltier plate.
Okay, and
Okay, we don't need more of these lines. We're gonna stop.
no, I'm asking what is the coolant. So if you
Oh,
need
what
to
is
replace
the coolant? It is this lovely bottle of stuff. It's coolants,
Okay.
polyglycol solution.
What coolant you put in the other machines?
I don't know. I have no clue. But it's, clear. I think it's just water in that one. Because I never need to change that one. Well, I need to change it once. I think it was just water.
That's it.
Alright, we good?
Done there. You're gonna clean it. So we're gonna just. Get some paper towels on that. Yeah. Soak up as much as you can. Oh, that's gonna be such a mess.
I feel bad for you, Patrick.
Mm.
It's funny because I go by Patrick, so the more that you say Patrick, the more it's confusing to me. I know everything is my first name, Nevin, but I go by that, so every single time you say it, I'm like,
What, you
no.
talking to me? I'm gonna be fine. I don't know what you're talking about.
It also gives him plausible deniability in a way. He's like, I thought you were talking to the technician.
Yeah. Yeah. Well, your middle name's Patrick?
Yeah. It's very confusing because I sign everything with Patrick, and then people see it and they have to ask, but yes.
That's a great middle name. The best.
That's what my father thought, that's for sure.
Yeah.
Can I remove this to clean?
Oh, yeah. Feel free to do that. I'm just going to collect lots of data. We'll clean up and we'll go through that.
So, am I good on?
Yeah, I don't think we're going to be doing anything training-wise, really.
All right.
Oh, I guess if you want to take a picture of it, we can set this up on
Okay.
the thing. But you don't need that in the video. I mean, unless you really want it in the video.
I don't.
I'm going to let him clean this first. So.
Yeah. I'll put it in the video because I'm not gonna remember none of this. That's why we take videos. What?
Yeah, the downside is we have like a 3-hour video and then you don't know where anything is that you need, and you have to watch a 3-hour video to figure out.
Yeah, but that's why we have Justin to watch the video and take notes. Yeah, exactly.
I see there's a clear hierarchy of here.
Oh yeah. Oh yeah. We just keep giving stuff to people until we
Oh,
lose
did it
it.
get under it? Here, disconnect them.
Is that a tripod?
No, you can just flip it upside down.
Whose tripod is that?
Oh, that's city light. Yeah, crazy.
Why? Where was that tripod? No, I'm being serious. Why would you make me do this all day?
Because there's no holder in the tripod.
Then why did you bring the tripod? So you're telling me that that's just there for the fun of it?
I was about to fight somebody. I don't know who it's gonna be.
It was fun watching you hold it. That's for like 50 or 50.
Tanky, leave the room. Somebody's about to get fought. Come here, Justin. Yeah.
Oh, awesome.
Uh-huh.
If you don't have money to buy one professional camera trip for this kind of training.
That would've been, that would've been good too. We'll put it on boss, it'll be fine.
Everything.
That will be my next item.
Huh?
That will be my next item to buy.
Yeah, you should buy at least a
What are you
private
buying?
book with the
I'm
camera.
being serious. Why?
I'm sorry?
No, why?
Why to buy it?
No, I'm not talking to you.
I'm not talking to you.
You know, HR is gonna get involved in
That's
something.
the idea.
No, this thing can easily revolve to HR again.
I'm
Couldn't do that on a tripod, huh?
Yeah, we need a professional.
I would go ahead and stop the video.
yeah.